Okay, so this first topic we're going to look at in our radicals unit is just simplifying radicals of like different roots or different indexes to like 2, 3, 4, not just square roots, and doing operations with them. So first, to simplify them, the important thing to know is like your perfect squares like 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Most of you already know those, but the cubes and fourths are harder to remember. But it's just like 2 times 2 times 2. The cube root of 2 is 8. So just remembering that. And when you're finding the square root or cube root of a variable for perfect squares, it has to be a multiple of 2, the exponent. For perfect cubes, the exponent has to be a multiple of 3. And for a perfect fourth, it has to be a multiple of 4. So pretty much you're going to see what squares or cubes or fourths go into the number, and we simplify it that way. So for example, if we look at the square root of 72, so if there's nothing in the index here, it's assumed to be a 2. So we're going to think of what perfect squares go into 72. So in this case, it's 36. So I like to rewrite it as 36 times 2. Now the square root of 36 is 6. So that's going to come out in front, and you're left with the square root of 2. For the cube root of 56, you're going to think about what perfect cubes go into 56. So in this case, it's 8, and the cube root of 8 is 2. Now we have our variables. So 50, we want the square root. So we know that 25, so I'm going to rewrite a bunch here. 25 goes into 50, so it's 25 times 2. And I always like to rewrite all my variables so that they have even exponents. So we need these to be divisible by 2 to be able to take them out for perfect squares. So x to the fourth times x is x to the fifth, but x to the fourth can be taken out because it's a multiple of 2. And y to the sixth just stays the same because it's already a multiple of 2. So we're going to take out the square root of 25 as 5. We're done with that one. The square root of x to the fourth, you're going to always divide it by whatever your index is. So 4 divided by 2 is x squared. And 6 divided by 2 is y cubed. And then in the square root, we're left with 2x. Now for the fourth root, it's the same type of thing. So we want to think of what perfect fourths go into 32. And in this case, it would be 16 times 2, because 2 to the fourth is 16. And then we need our numbers to be, or our exponents to be divisible by 4. So we can do x to the 12th. 12 divided by 4 would be 3. And that would leave you with x cubed. And then y to the 8th would leave you with y cubed. So the fourth root of 16 is 2. Done with that one. 12 divided by 4 is x cubed. 8 divided by 4 is y squared. And then under the fourth root, we're left with 2x cubed, y cubed. So that's how we're going to simplify all of our radicals. So we're going to be using that when we do our operations as well. So when we're adding and subtracting, your first step is to simplify all of your radicals first, then find ones that have the same index and same radicand, so the number under the square root has to be the same, and the number here has to be the same. Then you add and subtract your coefficients and keep your radical the same. So for example, just look at it piece by piece. So 7 times the fourth root of 48. We want to see what perfect fourths go into 48. So in this case, it would be 16 times 3. The fourth root of 16 is 2. So we have 7 times 2 times the fourth root of 3. If you ever have a number in front, you just multiply them together when you pull something out. So that one simplifies to 14 times the fourth root of 3. This one's already simplified, so we just leave it. Minus 2 times the fourth root of 3. And then this one, we want to find the cube root that goes into 72. So in this case, it would be 8 times 9. So the cube root of 8 is 2. So 3 times 2 times the cube root of 9. So we have plus 6 times the cube root of 9. So in this case, the only ones we can add together are these. They're kind of like when we have like terms with variables and everything, but they have the same index and same radicand. So we're just going to do 14 minus 2 gives us 12 times the fourth root of 3, and that other one stays on the end because we can't combine it with anything. Now multiplying is a little easier, so if you have the same index, you just multiply your numbers together inside the radical, and then you simplify your answer. So you can do this with distributing. Sometimes we're going to have to FOIL, but these are all an index of 2. So we have 5, and then 10 times 5 is 50, minus 2 times the square root of 10 times 2 is 20. So we're going to simplify each one. 50, 25 goes into it twice. So we get 5 times the square root of 25 is 5, root 2. So we get 25 root 2 minus 20 is 4 times 5. The square root of 4 is 2. So we have 4 root 5. And we can't combine them because they don't have the same number under the square root. Dividing, we always want to just rationalize our denominator. So if there's just one number, just a monomial in the denominator, you're going to multiply it by whatever radical. So if it's like 3 root 2, multiply the top and bottom by the square root of 2. So just whatever's in the bottom to make it cancel out. And then if there's a binomial, you're going to multiply by the conjugate. So if it's 2 minus the square root of 3, we're going to multiply by 2 plus the square root of 3. Opposite side, you're flipping the sign in the middle because that'll make it cancel out. So for example, we have 2 over 6 minus the square root of 5. It's that binomial, so we're going to multiply by the conjugate. So you're going to flip the sign in the middle. So we're going to multiply the top and bottom by 6 times the square root of 5. So in the numerator, we're going to just distribute this 2 in. So 2 times 6 is 12, plus 2 times the square root of 5. In the denominator, I'm going to FOIL it out to show you guys, but we did talk about how there's a shortcut to this. So 6 times 6 would be 36. 6 times the square root of 5 is plus 6 root 5. Negative 5 times 6 is negative 6 root 5. And then minus the square root of 25. So we always get 36. These two cancel out, minus the square root of 25 is 5. So we get 31. So you always get the square of the first number minus the square of whatever, or just whatever's under the square root. So 36 minus 5 is over 31. Now, rational exponents are a way that we can convert back and forth between rational exponents and radicals. So in this case, if there's a 1 in the exponent, it's telling us that this is just our index. So like a to the 1/4 is just the fourth root of a, or 2 to the 1/4 is the fourth root of 2. Or you can have a number in the numerator, so that exponent is raised to that. So we're going to see an example of this. So k to the 7 over 2, you can rewrite it. The bottom number is your index, so it's the square root of k, and it's raised to the power up top. And then this one, we could rewrite it as a rational exponent. So it's x, your index is in the denominator, and whatever it's raised to is in the numerator. So with those, we are going to see some operations. So we can use exponent rules to help us simplify these down and then rewrite it as our radical expression. So for example, when you're multiplying, when you have the same variables, you add your exponents. So we have x to the 1/3 plus 4 over 3, which is x to the 5 over 3. And then to rewrite it as a radical, it's the cube root of x to the 5th. So we're going to be working on all of this, so come to class with any questions that you guys have.